Okay, so in this video, I'm going to go over section 8.3, which is preparing to estimate the population proportion. They start with talking about the general form of a confidence interval. So remember that a confidence interval is the point estimate of your parameter of interest plus or minus the margin of error. And then here they go further into margin of error as a critical value times the standard deviation of the statistic. Since we don't have the statistic, we're working, since we're working with the statistic and not the parameter, we're using what they're calling the standard error of p hat instead of the standard deviation. And so we're thinking about this as the point estimate plus or minus the critical value times the standard error of p hat, which is given by this formula here. So the standard error is this portion under the radical. So again, it's because I have p hat, not the population parameter. Z star is the multiplier that tells us approximately how many standard deviations away from the mean that capture the population. Okay, so this value here is where Z star, what Z star is estimating the number of standard deviations away. So we're going to use that formula for problems in the future. So it's going to kind of work into solving that formula, but really we're just going to plug in this lesson and finding out what Z star is. So beginning though, it starts with the idea of when can I use this formula? So the standard error formula will capture the population parameter and C% of all random samples selected from the population of interest when these three conditions are met. So the first condition is the random condition. And so the data must come from a random sample. And so remember, non-random samples are like convenience samples. So if I'm collecting data from the first 100 people that walk by, or if I'm sending in an email or ask people to answer a question or give me data, then those are not random. Ultimately, when you're doing these problems, if the sample is random, it'll literally say they collected a random sample in the problem. Okay, so if it doesn't say that the sample was random, that means that that condition wasn't met. The next condition is the 10% condition. The sample size must be less than 10% the size of the population. I think in one of the examples, they say like it was like birds or something, and they give you a number, and the number is relatively small. So if we're talking about people, right, and they choose 100 people, 100 is a drop in the bucket compared to the entire population, right? And so there isn't really a formula for the 10% condition unless they give you the population amount. So we'll look at an example that kind of does that so that we can kind of check that. The good thing about this condition is if it's not met, the capture rate's actually higher. So if I have a 95% confidence level, then it will result in samples capturing the parameter more often than 95% of the time, which is a good problem to have, right? It means that my samples are better than my confidence interval. And so we only have to check this when a sample is made from a finite population without replacement. So meaning finite means that I know the total. Again, without replacement means that everybody out and I don't return them back in to collect a new sample. So once I've asked somebody a question, I don't ask them again. Okay, so that's when this cannot happen. The last part is the large counts condition. So the large counts condition is where I have to check the sample size times p hat and the sample size times the conjugate 1 minus p hat. And those numbers must be at least 10. Remember, at least means that they must be greater than or equal to 10. Okay, so 10 or larger. So in the first example, we're just checking these three conditions. And then we're going to go into how to calculate Z star and then how to plug into that entire formula for our confidence interval. Okay, so I have this situation. The computer company wants to determine the proportion of defective computer chips from the day's production. A quality control specialist takes a random sample. So the fact that it says that it was a random sample means that this condition was met. Okay, so it has that word random. That means it was random. Of 100 chips from the day's production and determines that there were 12 defective chips. So if we think about production, 100 chips is likely to not be very much in terms of the entire population, right? So I don't have a finite population, right? They're producing a lot, and they're not telling me a number, means that it's going to meet that condition, okay? So it's not finite. I know it's going to meet that condition. And then he wants to construct a 90% confidence interval for the true proportion of the defective chips from the day's production. Are the conditions met? So remember that large counts, I have to figure out what N is and what P hat is, okay? And so N is the number of chips, right, which was that 100. And then P hat is the number of defective chips, so that was 12. Out of the total number from the sample, which was 100. So that means that P hat is 0.12. Okay, so 12% is that value. So remember that what we have to do is we have to check that this times that number times 100 is at least 10, and that number times its conjugate, so 1 minus that number, is at least 10. So we're looking at, for this one, N P hat and N times 1 minus P hat. And so these numbers must be greater than or equal to 10. So NP hat is 100 times 0.12, which is 12. That's good. And then this one we get 100 times 1 minus 0.12, which is 100 times 0.88, which is 88. So both of those numbers are larger than 10. So that means that, yes, it's met. So it has to meet all three. The second that one is not met, that answer is no. Okay, so for this one, it does meet the conditions for inference. The next example, we have a local college admissions officer that wants to survey incoming class of 500 first-year students. So this is the total number of the population. So we've got a finite population of 100 students. 500 students, sorry. The officer randomly selects 100 of them to complete the survey and finds that 45 are planning to major in liberal arts. The admissions officer uses the data to construct a 95% confidence interval of the proportion for first-year students majoring in liberal arts. So I missed this, so he randomly selects 100, so it is random. So if we're checking the finite population, so we want to see, does 100 divided by 5 meet the 10% threshold? And if we divide 100 by 5, 1/5 is 0.2. So that's 20%. And it needs to be less than 10%. So that means that this does not meet that condition of 10% of the population, which means that this condition is not met. So that means that no, the conditions for inference are not met. So I don't need to check the large counts because it doesn't meet the 10% of the population condition. Okay, the next thing that it talks about is finding the critical value, Z star, for constructing a confidence interval for a proportion. So I just chose a 92% confidence interval. So remember, that means that this portion here of the graph is 92% or 0.92 of 1. And so I want to be able to figure out what one of these sections of the graph is. So I want to find those tail values. So remember that to do this, what we're going to do is we're going to subtract that decimal from 1. So that means that The tails represent 8% of the entire population. I want to know just one tail though in order to find the z-score, because this is negative z-star and this is positive z-star. And so in order to find the appropriate z-score, I need to divide this number by 2. So that means that each tail is 4% of that graph, right? So one of these is 0.04, one of these is 0.04. So this value z-star is going to be the same on either side, right? It's positive or negative. So that means that when I'm looking at my z-table, I can look at whatever part I want. So remember that this means that when I'm looking on the inside, not the z-scores, right? The z-score is going to be my answer. I'm given a percentage. So I want to find whatever's closest to 0.0400, so within the center of the data. And again, I can look at the negative side or the positive side. That part doesn't matter. So if I look here, looking for something that is about, so my closest values are here. Okay, so that means that I know it's going to be negative 1.7. And then I want to choose which one of these ending digits are the closest. Okay, so I have 4.01% or 3.92%. So if I think about that, this 4.01 is the closest. So that means that Z star is going to be 1.75. Okay, so again, I'm looking at those values. To figure out what Z star is. Okay, it could be positive, it could be negative, right? I'm adding and subtracting that same Z score. Okay, so we'll look at that one more time when we get into the next problem. In the next slide on this, they start to talk about common values. So if you see these a lot, they give you the more precise value using technology, but they don't show you the technology. They're just giving you the 90, the 95, and the 99 percentiles. And then they give you a t-table from a t-distribution, which is something later in stats, for common Z-star values. So if my confidence level is 50, 60, 70, and so on with these values here, I would use that number on top, and then I don't have to look at the t-table. Okay, so this is, sorry, z-table. So using these t-table values will get us away from the t-table. Z-table and having to do what we just did in the last problem. So I'm going to do an example where we're plugging into the big formula from the beginning. We will use both methods, finding Z star. In the assignment or the quiz, it uses the Z table value. However, if it's a number on the T table and you just look it up, you're finding the number that's closest to it. So this one is a 90% confidence level. So we're looking at 90%. So 1.645 would be Z star. We're going to get something that is different using the Z table, but really close. And so it should be obvious which answer it is if you're using that, even though it has it only to the hundredths place instead of the thousandths. So in this problem, we have a local school board that wants to determine the proportion of households in the district that would support a proposal to start the school year a week earlier. They ask a random sample of 100 households whether they would support the proposal. So we've got random, right? They give us 100 for a whole school district. So 100 is probably not a lot of kids. There's more than 100 students in one elementary school, right? So this is telling us that it's probably a lot less than 10%, which is why they're not giving us that finite level. And 62% of households state that they would. So assuming conditions have been met, what is the 90% confidence interval for the true proportion of households that would support the proposal? So if we check the large counts, if we do n, which is 100, and p hat, which is 62 out of 100, or 0.62, and p hat is 100 times 0.62, which is 62. And then n1 minus p hat is 100 times 1 minus 0.62, which is 0.38. So 100 times 0.38 is 38. Both of these are greater than or equal to 10. So that means that that condition is met. So if we're looking at our formula, we know p hat. So p hat is 0.62. 0.62. Move this up. Plus or minus, we need to figure out what z star is, times the square root of 0.62 times 1 minus 0.62 divided by 100. So our last step is to find z star. Remember, we talked about using this from the t-table. Z star is 1.645. Just a reminder of how you figure out z star using the tails. So if this is 0.9, that means that the tails together are 1 minus 0.9, which is 10%, so 0.1. If I divide that by 2, that means that 5% is the value for each. Oops, I left out a 0. Is the value for each of these tails. So that means that on the z table, I'm looking for as close to 0.0500 as I can find inside. So 0.0500 would be between these two values. And actually you can see from there, it's perfectly between. So I would just go with the larger z score. It doesn't really matter. I mean, you can look at what the options are because it will have one of them. So I would say it's negative, it's 1.65 as my value, rather than overestimating with the 4. Okay, so again, either one would be appropriate. It's a multiple choice question where they don't calculate it, so you can see what it's supposed to be. So 1.65 is the value that we'll use. You can see from there that it's actually perfectly between, and they use 0.645 when they go to that next decimal value. And so this is the answers that they're looking for in here. We aren't actually calculating the value of the length of our interval.